Hello friends, welcome to VK Lectures. In this lecture, we are discussing the thermodynamic equilibrium and variables from statistical mechanics. Any thermodynamic equilibrium is associated with certain variables. Okay. Now, when we say this thermodynamic equilibrium can be of thermal equilibrium, which accounts for the thermo in the thermal. Dynamic is basically the mechanical equilibrium, and also it is chemical equilibrium. So when these three parameters associated with are in equilibrium, we say that a system is in thermodynamic equilibrium. Thermal means the heat energy, that is generally related to the energy of the system in equilibrium, generally the heat energy, where we need to understand that T1 is equal to T2. Just let us take the example of a system with two compartments. We say that both are in thermal equilibrium when T1 is equal to T2, and here when it is in thermal equilibrium there is no heat exchange. Now coming to the mechanical equilibrium generally related to the volume. When the volume is same, that means this thermodynamical equilibrium has same volume V1 and V2. There is no exchange of volume. We say this pressure is constant. It is related to volume. We say there is equal pressure. Similarly to the chemical equilibrium, there is no transfer of particles, N1 particle and N2 particle. Okay. Now there is no exchange of particles. Here there is no exchange of the volume. This as particle exchange is determined by a term called chemical potential. So the chemical potential is mu, and mu1 should be equal to mu2 if they are in chemical equilibrium. So now another term or variable associated with thermodynamics or thermodynamical equilibrium is the entropy. Entropy is the disorder, and it also tells you about the direction of the energy change. Yes, that's about the entropy. The Boltzmann, there's a relation between the entropy and the number of microstates. So entropy and microstates. Now this relation was given by Boltzmann, Boltzmann, he suggested that the entropy will be a function of omega, where omega is the microstates. The microstates, and that's given by S is equal to Kb log omega, where omega is the microstate and S is the entropy, Kb is the Boltzmann constant. So S is entropy and Kb is Boltzmann constant. In statistics, we know that the concept of equilibrium is based on the most probable state. For example, when we say that the system is in equilibrium, so this is the term, the system is in equilibrium. This means that there is a most probable state when a system is in equilibrium, it suggests that the most probable state is having the maximum probability. Or system is in most probable state. When the system is in most probable state, the system is said to be in equilibrium. That means for any system, if the system is having the most probable state, any system will have the most probable state, and if the system is in that particular state, then this is called, it is said to be in equilibrium. For example, we have seen in earlier that if there are 5 particles and 2 states, then you can arrange them in 5, 0, 4, 1 and 3, 2. So these are different ways we can arrange the particle. Then this is 5C0, which is equal to 1. This is 5C1, which is equal to 5. And here we have 5C1 or 5C4 is anything. Yeah, 5C1. Let us take 5C2 here, which is equal to 10. So this is the maximum probability. This is having 10 number. 10 combinations are possible for this. So next one will be 4, 1, which will be equal to 5C1 or 5C4. 1, 2. Yeah. So this is already done. 2, 3 is already done. So this is the maximum probability, which means that the system with the 5 particles. So if I have a system with the 5 particle and there are only 2 states, okay, and this is having just 2 states, that means some of them will be in state 1 and some of them will be in state 2. These particles, some of the particle will be in state 1 and some will be in state 2, and this is in general can be written as the 3, 2. So some of them are in first state, some of them in second state. That means 3 of them in first state and 2 of them in the second state. Okay, so this tells you that this particular state 3, 2 is having maximum probability. And in equilibrium, if the system is in equilibrium, the system is having, or system is in state 3,2. So when beforehand, that means if you know the system, you can find out the most probable state. This is most probable state. Most probable state. So if you know the system, you can find out the most probable state, and we can also find out that in equilibrium the system will be in this particular state, not in any of this state. You can find a system in 5,0 and 4,1 also, but it will not be in equilibrium. This you can wind or put it in terms of temperature, energy, number of particles, okay, etc. There what we can do, there are 5 particles and 2 energies, which indicates 2 states, or 2 temperatures. At temperature here there will be different temperature, at this here different temperature, and number of particles. In a region you may have more number of particles, and in another region you may have some other number of particles, just like we discussed about 3-2 state. Now let us understand thermal equilibrium. In thermal equilibrium, we are assuming that we have 2 states. So states is equal to 2, and the energies are E1 and E2. So here the 2 states 1 and 2 is having the energy E1 and E2, and we can also write the total energy is equal to total energy E is equal to E1 plus E2, and so total energy E is constant, and from here we can write that dE, that is the small change in energy, is equal to 0 because it is constant. Okay, so now dE is equal to 0 means my dE E1 plus dE2 equal to 0. This implies dE1 equal to minus dE2. That means if the energy is increasing, then the of energy state 1 is increasing, then the another one should decrease. Here we can also get that dE1 by dE2 will be equal to minus 1. Now let us understand, or let us take the number of energy microstate, number of microstate in the microstate in let us say state or macrostate 1. So there are 2 macrostates. This is the 2 macrostates. Okay, and it will have microstates, that is the number of particles. So number of microstate in this macrostate 1, let it be equal to omega 1, and we can also write omega 1 be a function of E1, and number of microstate for macrostate 2. Macrostate 2 is given by omega 2 E2. Okay, so first one corresponding to the omega 1 correspond to number of microstate in the macrostate 1, and the number of microstate in macrostate 2 is omega 2. Now this one represent number of microstate with energy E1, and this one represent number of microstate with energy E2. Okay, so now coming to the entropy can be added. So corresponding to omega 1 you have entropy S1, and corresponding to omega 2 we have the entropy S2. Then total entropy S is equal to S1 plus S2, and the total number of microstate will be equal to omega 1 into omega 2. So this gives us the total number of microstate is the total probability when considering the thermodynamics. You can write 1 by omega 1 times dou omega 1 by dou E1 plus, or you can write it equal to 1 by omega 2 into dou omega 2 divided by dou E2. So this is the equation relating to the thermodynamic equilibrium. So 1 by omega 1 dou omega 1 by dou E1 plus 1 by omega 2 into dou omega 2 by dou E2, which means for any equilibrium, either it is mechanical equilibrium, thermal equilibrium, or a chemical equilibrium, there must be some quantity which is constant in both the states. So here this is the constant thing, so some quantity, so this is the idea, some quantity in system 1 is equal to the same quantity in system 2. For example, this one 1 by omega 1 dou omega 1 by dou E1. For it cannot be that in system 1 temperature is same and it is related to some energy in system 2. No, if this is temperature in system 1, in the second system also it should be temperature n. Only then these two can be called in equilibrium. Okay, so this is if the temperature are the same for both of the system, then we say that it is thermal equilibrium, it is thermodynamically in equilibrium, with the temperature being the quantity which has been in the which is equal to which is equal in both the system. So for thermal equilibrium, we have energy which is constant in both the system, so E1 and E2, which implies the quantity which is same is beta 1 is equal to beta 2. And what is beta? Beta is equal to dou by dou E of log omega. So beta 1 which corresponds to the state 1, and beta 2 which corresponds to state 2 with energy E2. Beta is given by dou by dou E of log omega. Now that's for the thermal equilibrium. Corresponding to the mechanical equilibrium, which deals with the volume change. Mechanical equilibrium, we have two states, and the states will have different volume V1, V2, and the quantity and the pressure has to be same. P1 should be equal to P2 with different volume mechanical equilibrium. So but the pressure has to be same, and the quantity is eta given by dou V of log omega. So this is the eta, and the pressure P is given by eta kBT. Now here, with respect to energy, we are separating the two states. So beta 1 is the constant quantity, and thus beta is a function of E, or it's a derivative of E with respect to the macro states, sorry, the number of micro states omega in that particular state. Similarly, the eta, which is the quantity for a mechanical equilibrium, here we have the volume change, so dou by dou V of the total number of microstates, log of the total number of microstates. And for the chemical equilibrium, we know that it is the chemical potential, so mu1 and mu2, and it is related to number of particles. If the first state is having number of particles n1, and the second state is having the number of particles n2, then the quantity zeta, which is given by, which will be a function of log omega, but here it is with respect to dou n, so dou by dou n of log omega. So here the quantity mu1 should be equal to mu2, and what is mu is given by zeta kBT. Looking into the thermodynamic equilibrium more closely, let us see what we can get out of it. So thermodynamic equilibrium. Thermodynamic equilibrium says that d by dE of log omega is equal to beta, which is nothing but 1 by kBT, where kB is the Boltzmann constant T, this is kB T. T is the temperature. Now omega, as you know, it's the number of microstates. E is the corresponding energy. Now this is also equally true that dE is nothing but dQ, that is the change in energy is the change in heat, that is the heat energy, and this is equal to TdS, where ds is the entropy. S stands for entropy and Q stands for heat. So change in heat is TdS, okay, T times ds, or we can also write this ds equal to dq by t or dE by t. Now this is let this be equation number 1 and this be 2. Now 2 divided by 1, let us take 2 divided by 1 gives us what is that? So partial derivative dou s, this one, by here we have dou by dou e of log omega, so dou by dou e of log omega is equal to, the right hand side that we have is dE by t divided by 1 by kBt. This kBt. Now let it be dou e, partial derivative. Now here becomes dou s by dou of log omega is equal to, or 1 by dou e times dou of it's not there, so when it comes to the other side it becomes in the denominator, so that becomes kb will go up, so dou s is equal to, only term that is remaining is kb, and from this you can write dou s is equal to kb 2 log omega. So you can also bring this kb inside, where you can write dou s is equal to dou times kb log omega, and from this you can write s is equal to kb log omega. So s is equal to kb log omega. So this is the equation for entropy. S is entropy, we already have said. This is number of microstates, or number of ways of arrangement. So entropy S is equal to kb log omega, where omega is the number of microstates. Now for a system we can find omega, which is equal to basis whole power n. We have seen how we deal with coins and two states or dice. The basis of all these events. And now let us take for a spin half particle. For spin half particle, we have the basis. What is the basis? That is equal to 2s plus 1. So what is 2s plus 1? Basis is number of particles in a state, or this also indicates the available possible outcomes. Okay, so 2s plus 1, so that's equal to 2 into s is half plus 1, so that is 2. So number of outcomes is 2, that means number of particles in a state is 2. Now for n particles, the omega, that is the number of microstates, will be equal to basis whole to the power n, that is 2 to the power n. Now what is the maximum entropy? Yes is equal to kb log omega, that's equal to kb log of 2 to the power n. So that's equal to the power n means log 2 to the power n means n log 2. So kb into n log 2, n can be taken out, so n kb log 2. So this is the entropy for spin half particle when there are n particles. Okay, so second one, let us also take for spin 1 particle. For a spin 1 particle, the basis will be equal to 2 into 1 plus 1. 2s plus 1 is equal to 3. So omega is equal to 3 to the power n if there are n particles. So s is equal to kb log omega is 3 to the power n. So this gives us n kb log 3. Now here is an interesting note to make. So if when you go from 1 to 2, you can say the number of microstate is increasing. In this case there was only 2 bases was 2, and in spin 1 particle the basis became 3. Now the important inference, so depending on the number of bases, omega will become 2 to the power n, and for spin 1 omega became 3 to the power n. So the important conclusion is, higher the microstate, higher the microstates, the higher is the entropy. It's obvious, higher the number of microstates, larger will be the entropy and disorder. More disorder will be the state, because you have more number of macrostates corresponding to that microstates also. Here we are going to understand the relation between entropy and probability. Now, before the understanding the relation, let us understand what are this probability and entropy here. Now, these are different states with the energy E1, E2, E3 and etc. up to En. The number of particles N1, N2, N3 etc. up to En. Okay. Now let us write the last term being S. Okay. This is N S. This is ES and NS. Okay. Now the probability of finding the particle in energy E1, let that be equal to P1. Energy of finding the particle in P2, that means P2 is the probability of finding the particle in energy E2. Okay, so here this will be P3 and here you have PS, any random number S. Okay, assume there are S states, so from 1 to S. Okay, now this is the first state, second state, third state, and this is the S state, the last one. Okay, now these are the energy corresponding to that particular state. So the first state is having the energy E1, E2, E3, E4, and the first state is having number of particles, N1 particle in the first state, N2 in the second state, N3 in the third, and finally NS in the last state. Or now the total number of particles, that means the total number of particles is N1 plus N2 plus etc. up to NS. Let this be equal to capital N. So this is the total number of particles, and for any state PS, for any state the probability is given by the NS, that means number of particle in the S state divided by the total number of particles. So this is the probability PS and this is the N, and you know that is S, which is the entropy, that is given by KB log omega. Omega will be the number of microstates, and the relation connecting this S and PS is given by S is equal to minus KB sum over S into PS log PS, minus KB sum over S, PS log PS. So we also have to remember that S is a positive quantity, because log of PS is the probability, this will be always less than 1, so log of something less than 1, which will be equal to negative, so negative and negative gets cancelled, and KB is a Boltzmann constant which is positive, so S is always a positive quantity, and this is the formula connecting the entropy and the corresponding probability of the microstates.